at the limit comparison test, and the relation, or the rule, given the sum of a sub n, as n goes from 1 to infinity, and b sub n is the parent EBM of a sub n. So a sub n and b sub n are both greater than 0, and the limit, so this is the important, or an important component, of a sub n divided by b sub n, so that's a new component here, new idea, is equal to L. L has to be finite and positive, right? So it can't be infinite, it can't be some negative value, and it has to exist. Then the two series either converge or diverge, right? Both, all right? So let's get a parent EBM. Double tap there. So the parent EBM is going to be b sub n equals, now we take the ratio of the leading coefficients. I'm sorry, I'm thinking of the wrong thing. Take the ratio, I was thinking asymptotes for a sec there, just force a habit. The ratio of the terms with the highest exponents, top and bottom, but then strip away any coefficients that might be there. All right, so it's going to be n to the fourth over 4n to the fifth. If I strip away the 4 and just reduce n to the fourth over n to the fifth, I get 1 over n. Okay, so that's what we're going to create in terms of a ratio. Now, a sub n has to be greater than 0. Now, we could look at the picture. Now, a sub n itself is a sequence of values, but we could also look at it in the form of a function. All right. So now we're not going to be using a limit an integral of some kind of function. We are going to be, I almost said we're not going to be using the limit comparison test. We are going to be using that. But what we can do is treat, the way we've been doing for other problems, treat this as a function. You know, let's see what's going on with the function that passes through the points generated by the a sub n sequence. So x to the fourth, and it's a kind of, it's kind of a lot to type in, but it's worth it. 5x to the fifth minus, 4x to the fifth. I crossed it off and then I couldn't see it. Minus x to the third plus 7. All right, so just double checking. Looks like we got it. Just do a zoom 6. I just wanted to verify that it would be positive for the relevant values of n, and it looks like it's above the x-axis, doesn't go below it. And I can take a look at the table, and it looks like it's asymptotic, which hopefully you kind of recognize based off of pre-calc knowledge. All right, so it looks like we're in good shape there. All right, so we check that condition. Oops, sorry, I hit the wrong thing. This seems to be a video for me hitting the wrong thing. Let me get rid of this stuff so I don't make the mistake again of thinking that coefficient was a 5. All right, so what we're going to do is we're going to find the ratio of a sub n to b sub n. We're going to find the limit as n approaches infinity of a sub n over b sub n. All right, so it's the limit as n approaches infinity of n to the fourth plus 10 over 4n to the fifth minus n to the third plus 7 over 1 over n. All right, the top fraction being the a sub n, so this, and the bottom fraction being the b sub n. All right, so a little keep change flip action. We're going to have the limit as n approaches infinity. We're taking this and multiplying it by n over 1. All right, so in terms of what's being accomplished here, you actually take a close look and you realize it's actually kind of cool. We just created an instance where the numerators, I don't think I wanted to delete the whole thing. The numerator's high power was just increased by 1. All right, so what does that do for us? It changes the nature of the limit. All right, because when I'm looking for the limit of a rational expression where, well, limit of a rational expression related to a rational function in a lot of cases, if the exponents are the same, I'm looking at the leading coefficients and the ratio of those leading coefficients as the limit. All right, so this will give me 1/4. All right. So we got something that is both finite and positive. All right. So suppose a sub n, b sub n are both greater than 0. Check. I mean, actually, kind of check. We checked the a sub n. We didn't check the 1 over n, but we know that that function looks like this. All right, if you graph y equals 1 over x, so it's, just from experience, we know that that checks. All right, the limit checks out. L is both finite and positive. Then the two series either both converge or both diverge. All right, so we still haven't established convergence. You can't look at this 1/4 and say, oh, so that means therefore it converges. All right, when I first learned this technique, that was my misconception. All right, what we need to do now, since we know that they're both going to converge or both diverge, all right, and what I mean by both is we have the original, that's the sum. Let me actually make that ellipse look a little bit better. That's the sum of a sub n. We're also going to get this, we also have the sum of b sub n, which is the sum as n equals 1 to infinity of 1 over n. So we came into this problem being like, well, we don't know whether this converges or not. All right, we evaluate our b sub n over here and determine whether that converges based off the limit comparison test. We can make a determination of whether a sub n converges, all right, or at least the sum of a sub n. All right, and so what we're looking at here is a p-series. It's fortunate that we took the time to investigate those p-series, because now we have something that can save us time and energy of evaluating, because if you remember, we used the integral test to take care of those situations. So this is a p-series with the p-value equal to 1. All right, so the only thing that you have to remember is, well, what does that mean? Well, if the p-value is between 0 and 1, the series diverges. If it's greater than 1, then it converges. So the sum of b sub n from n equals 1 to infinity diverges by the p-series test. And so we can therefore conclude that the sum from n equals 1 to infinity, well, once we designate this as the sum of a sub n, if we do it in a reasonable way, I'm going to just kind of clean that up a little bit. We won't have to write the whole thing again. So a sub n diverges by the limit comparison test. All right. So by now you've probably recognized, I mean, I stated it explicitly, but even if I didn't, you would have recognized that I'm pretty big on the abbreviations. So if you want to also be big on the abbreviations, that's great. I'll say the same cautionary piece of advice that I gave when I first started talking about abbreviations, and that is your next teacher may not be fond of them, so just be careful. going forward, but for me, abbreviations, as long as I know what you're talking about, we're good. And there are the little things like when I say AST, I mean alternating series test. We haven't gotten there yet, but that never means arithmetic series test. All right, so you'd have to write that one out. So looking at the next one, we're going to identify the parent EBM, which again, and I might as well just kind of take it in terms of coming up with the parent EBM. I'll take it a little slower this time, just to kind of really drive this point home, because you see it keeps coming up over and over again. All right, so the EBM you get by taking the term with the highest power on the top of the fraction and on the bottom of the fraction and making a ratio out of it. So this is the EBM. Y equals, well, it wouldn't really be Y. EBM would be Y equals if it were a function. So in this case, it would just be 1 over n to the third. The parent EBM is what you would get if you stripped away any constant multiples or addition subtractions that existed. All right, so for example, if this were 1 over 2n cubed, I would strip away the 2. If this were, let's say, 1 over n minus 2 cubed, I would strip away the minus 2. All right, so any transformation upon your EBM makes it the parent function. All right, so in this case, it turns out that the parent EBM is the same as the EBM itself. So b sub n is going to be 1 over n cubed. Now, a sub n, we learned in the last one, it's in our best interest to write it as a sub n at some point so that we can make use of that notation. All right. Now, you'll notice that this one starts off at 2. So I'm going to designate my parent EBM summation as, or having the same bounds, right? And we learned, maybe it was last video or 2 videos ago, that that's all well and good. You can have a lower bound of whatever you want as long as the upper bound is infinity, right? So if we wanted to, we could rewrite this series so that it starts off as a 1. You'd expand out what you have here. And I'll just do it really quickly. I'll give you the short version this time. You put in a 2, you get 1 over 2 cubed minus 2. Put in a 3, 1 over 3 cubed minus 2. 1 over 4 cubed minus 2. So that would be 1/6, 1/25, 3 cubed, yeah, and so on. But we're really kind of more interested in the first line. All right. So I would be asking myself, if I wanted to write this as an expression starting with an n value of 1, and actually let me get rid of the commas and make them plus signs, because ultimately they are sums. And I wanted to go from n equals 1 to infinity, I'd be thinking to myself, all right, in every case we have a 1, we have a power of 2, we have a minus 2. The only thing that's concerning is what's being raised to the power of 2. I may be saying, okay, if I'm starting off with a 1 and I want to end up with a 2, what would have to be in here? Well, it's got to have an n in there. It's just a question of, if I want it to be a 2, do I do 2 times n? I could try that, but if I do that, then the second one will be 4, then 6, and that's not what I want. Or I could do n plus 1. All right. So n plus 1, that works out beautifully. All right. You plug in a 2, you get a 3. You plug in a 3, you get a 4. Now, that would be my a sub n. Now, if I wanted a b sub n from this, my parent EBM would take the 1 on the top and divide it by the n plus 1 squared on the bottom. But again, stripping away anything that's either added to the 1, subtracted from, any constant multipliers or sums or differences, any transformation imposed upon the variable. All right, so this would still be a 1 over n. Oh, it's cubed, sorry. I was trying to make that a quick fix. I think I got to bring it in and surgically alter it. There we go. All right, so it'd still be 1 over n cubed. All right, and then you'd carry through the remainder of the process from here. So you'd have the sum from n equals 1 to infinity of 1 over n cubed, and then you'd go from there. All right. And you can investigate, you can apply the technique that I'm about to apply with the expression written in its original form with these new expressions and verify that it works out the same way. All right, I promise you it does. All right, so what we're going to do is continue working with the really it is a transformation, the cleaner version. All right, so limit as n approaches infinity of 1 over n cubed minus 2 over 1 over n cubed. Limit as n approaches infinity of n cubed over n cubed minus 2. A little keep change flip. The powers are the same. That's the whole point behind this. By choosing the parent EBM, we're creating an instance. That's the cleverness behind this. We're creating an instance where we're able to manufacture a rational expression where the high power top and bottom are the same, which leads us to being able to determine a finite limit based off the ratio of the leading coefficients, which in this case would be 1. So the limit exists, conditions are met, right? We have positive functions, I believe, yeah. If you plug in a 2 for n, you get something positive. You plug in a 3, you get something positive. If it's less than 2, then you get a problem, but that's irrelevant. All right, so we have all the positivity that we need. 1 over n cubed is positive for the values of n that are greater than or equal to 2. And the limit is finite and positive. So we're good there. So now we go to this condition. The two series either converge or diverge. All right, so it becomes a question of, okay, well, which one do I want to work with? I think the answer is obvious because we went down this road because we didn't know the answer to this question, but we do know the answer to this one. This one converges by the p-series test because the p-value is greater than 1. All right, and so we know that the sum of b sub n is going to converge, and since they go hand in hand, as stated by the limit comparison test, we now know, therefore, the sum as n, from n equals 2 to infinity of a sub n, which I can now use that notation because I stated it over here, converges. Converges? I don't think so. Converges by the limit, not the p-series test, the limit comparison test. All right, so a lot of interesting stuff, but you can see how everything that we're learning now is building off of something that we've already learned. So, if it means you got to go back and review some things, like p-series seems to be coming up over and over again, and p-series is built off of the integral test. Yeah, you might want to spend some time looking at that stuff.